power transformer rating. The transformer rating can be classified: body rating, current rating, and then Bowen rating. VA rating or Bowen rating. So current rating is equal to the Bowen rating divided by body rating. So that this is a transformer, primary winding. So primary current I1, primary number of turns N1, primary voltage V1. Secondary current I2, secondary number of turns is N2, and secondary voltage V2. So flux are passing through. When you connect the transformer to the primary winding, the magnetic flux will link to the secondary winding and the voltage will be produced. So the V1 by V2 equal to N1 by N2 equal to I2 by I1 is equal to A. So the V1, the primary voltage divided by secondary voltage is equal to primary number of turns divided by secondary number of turns equal to secondary current by primary current is at A. A is a turn ratio. So the voltage input in the transformer can be calculated by this formula. EIMA is equal to 4 by 44 Fn pi maximum. So EIMA is a root mean square voltage, A is a frequency, and number of turns, pi is a flux. So flux can be calculated. Flux is equal to P multiplied A. So P is a flux density, this law, A is a cross sectional area meter square. So that when you connect the transformer to the supply, so without connecting the secondary at the low and the low, so this is a no load voltage, and so this is a V no load. When you connect the load to the secondary winding, so this voltage is a V full load. So the difference between the no load voltage and full load voltage is the voltage regulation. The percentage voltage regulation can be calculated by the formula V no load minus V full load divided by V full load into 100. So then we connect the transformer to the supply. So this is the transformer here. So this is the transformer called the core length is the A, number of turns is N. The current waves is I. So A multiplied I is equal to H multiplied L. So in this case, N is the number of turns, I current, A is the magnetizing, A is the length of the transformer magnetic path. So when you are connected as transformer magnetic path is a separate magnetic path. So in this case, Ni multiplied N is equal to summation H multiplied L. So A is the length of the magnetic flux, magnetic circuit. So A is a magnetizing force. Magnetizing force can be calculated by the formula B equal to mu multiplied H. So B is a flux density, mu is a permeability, A is a magnetizing force. So then in this case, mu can be calculated mu 0 into mu R. Mu 0 is a relative permeability of the air, 4 by 10 power minus 7, and mu 0 is a permeability of the air, 4 by 10 power minus 7. Mu I is a relative permeability. So those are the equations to calculate the transformer voltage and magnetizing. And based on the those formulas that we will calculate this program. So this is the core. So number of times 350 Tesla. This core length is a 1250 millimeter. Air gauge is 0.15 millimeter. Flux density is a 1.105 Tesla. And we have to calculate mu out of the C is a 1800. So we have to calculate the current. So in this case, there are two parts here. Ni is equal to HL. So in this case, this is the two parts. This is iron core magnetizing and iron core length, and air gap magnetizing and then air gap length. So then Ni equal to HL is equal to H iron, I iron, L iron plus H air gap, L air gap. So this is for the two parts, iron core magnetizing and iron core length, and air gap magnetizing and air gap length. Ni is equal to HL, H iron, L iron plus H air gap, L air gap. So number of times 350 current. So in this case, HI is P by mu 0 mu R. HA is P by mu 0. So P is already given the 1.105. Mu 0 is 4 by 10 power minus 7. Mu I is 1800. L iron is 1250 millimeter divided by 1000. P is 1.105. Mu 0 is 4 by 10 power minus 7. L A is 0.15 millimeter divided by 1000. By solving this one, you got the I is 2.1 ampere. So another one is the losses in the transformer. When you connect the transformer to the supply, there are two kinds of losses. One way is the iron loss, another way is the copper loss. Copper loss is the primary winding copper loss plus secondary winding copper loss. Iron loss is the eddy current loss and hysteresis loss. Eddy current loss is that when you connect the transformer to the supply, the small magnetizing flux are flowing in the core. So this is the eddy current loss. Hysteresis law is that you connect the transformer to supply, the transformer will be magnetic, become the magnetic. So that the power required to become the magnetic is the hysteresis loss. So so that we can draw the transformer equivalent circuit diagram. So this is the magnetizing co-equivalent, magnetizing equivalent, primary winding, secondary winding, primary winding, resistor, inductive reactance, secondary winding resistor, inductive reactance. So primary voltage, secondary voltage. So that in this case, our primary resistor by secondary resistor is equal to primary inductor by secondary inductive reactance equal to A square. A is equal to N1 by N2. So therefore, this secondary resistor RS refer to primary side. So you can calculate RS there is equal to A square RS. Secondary inductive reactance refer to primary side. HS there is equal to A square AS. And therefore, the whole secondary resistor inductive reactance refer to primary. So that will be RS there ASS and then RB HB. So that we can add the primary resistor as primary, secondary side resistor refer to primary. RE is equal to RB plus RS there, so that RB plus A square RS. And similarly, AC is equal to HV plus HSS, so HV plus A square RS. So that will be the transformer equivalent circuit. Okay, based on this principle, we calculate this problem. So R equivalent, H equivalent is at 0.3 and 0.40. RC is at 200 ohm, AC 200 ohm, primary voltage at 200 volt. So we have to find the IL, IC, IA is as a low current, IC is as a no low branch. So current flow to the RC and AC, go and magnetizing component, and to the current I, copper loss and iron loss. So we will solve this problem in another slide.